Hi, everyone. So today is going to be the last part in our three-part lecture series. I just want to take a quick moment and thank you all for coming with me on this wonderful journey and just right into it. So a lot of you have probably heard about the idea of first principles. And I'll just write this on the board in case you haven't seen it before. Especially when it comes to an engineering context. And you might be familiar with this phrase already, but I'll talk a little bit about it. The idea is that you take a problem, you reduce it down to its most basic elements, and from there you build up a solution. But even though this is something that's very popular in most circles nowadays, especially in Silicon Valley, you can kind of get an understanding as to why you shouldn't necessarily reinvent the wheel every time. I'm going to come up with a little bit of an analogy for this one. So let's say you were being tasked with producing an apple-based dessert of some kind, right? You had access to a kitchen, you knew the fundamentals, you knew how to make a crust. You knew all of these things intuitively as your first principles. How to make a crust, how to cut up apples, how to use an oven. You're not starting completely from scratch, but you're starting with something that is based entirely off of what your initial knowledge is. And you're going to create an original apple-based dessert. So you decide to figure out what the best kind of dough is. You mix up a few different samples, you put them in the oven, you run through this process a bunch of times until you arrive at a ratio between the flour and the eggs and the butter and all the other accoutrements that comes out where you want it. And then you think about trying to solve the problem. Well, if you're trying to maximize the amount of dessert you're serving, you might want to go for a rectangular tray. So you go for a rectangular tray, you have your dough in there, you have some kind of filling, you cut up your apples, you know how to make a sugar glaze, you run through this whole process, and you produce something that at the end of the day resembles an apple pie. But there's also another way to look at that, which is, let's say you know how to make pie, and you are tasked with the exact same problem of trying to make something that resembles, an apple-based dessert that serves as many people as possible. And that is how you start. You say, okay, I know how to make a crust, it's round, you put the apples in it, and you go from there, and you create something that is basically an apple pie. They both kind of arrive at the same answer, and visibly you could say you have your first principles dessert, which is this rectangular block of stuff, versus a traditional old-fashioned, little pie plate going on. I can't draw a pie very well, but we're going to pretend that's pie, and this mysterious wedge. They're both fulfill the same goal, which is creating an apple-based dessert that satisfies people and is relatively familiar and isn't too experimental, but the amount of iteration you have to do to create your first principles apple pie is a lot more than trying to make just a regular old boring, not really boring, I do like apple pie quite a bit, but regular old pie. And that's the big thing you have to balance when it comes to approaching things with first principles. There's the reason why this lecture is called historical engineering context or a historical engineering context is because not everything has to be reinvented from scratch. And sometimes there are very, very, very good reasons for doing things the way that we do them. In other words, the apple pie versus the apple cube, I guess you could call that. And today I'm going to talk about some of that philosophy and that viewpoint of not necessarily obeying first principles, but looking at doing things by metaphor or by comparison, and also learning from history, because those are the two most powerful tools in your toolkit for trying to solve any problem. Is what have other people done, and what is this most similar to? So. Let me just clean off the blackboard real fast, and we'll write those down before we begin. Two very important questions to ask, and the first two questions you should ask before you even start thinking about a problem. Because the big disadvantage with first principles, as I kind of touched upon earlier, but I want to get into, is that it requires iteration. Iteration is a repetitive process, but most importantly, it takes a lot of time, depending on how fast you can go from your first version to your next version, how long that loop is. And in things like software, which is really where first principles kind of derives itself from, it really comes from the Silicon Valley approach of just iterating your way to solving a new problem. It means you fail a lot. But the fact is, in software, you can iterate on that very quickly. You can go within the span of days or weeks. You can have something that's gone from an idea to a finished product, even if you're starting from first principles. But in the real world, not saying that software isn't the real world, but hardware is a very different world unto itself. That cycle can take months or even years. And that's why I talk about the idea of reinventing the wheel and having to ask yourself these two questions. Because if you've exhausted both of these and you say, well, I can't learn anything from history and I can't figure out a good way to compare this to some other problem that's existed, then I have to go through this iterative loop and I have to start solving it from first principles. These are the two things you have to exhaust, because otherwise you make the same mistakes that other people have made getting to the answers. Because both of these kind of touch upon answers that exist already. And they're not perfect. There's no situation in which you walk into something and say, this problem is exactly to a T, this problem has been solved before. It'll generally be that there is a problem that's very similar to this that's been solved, and I can apply that directly to what I'm dealing with. A really big example in this in history, and kind of a historical footnote more or less, but an important one nonetheless, is the turbo pumps on the V2 rocket. Wernher von Braun and his team were tasked with coming up with a system that would deliver propellant to the combustion chambers of the V2 rocket, and at a very high rate. And von Braun and his team thought about it, and they recognized that the most reliable way to do that already existed. That the pumps that were used by fire departments all across the country, Germany at the time, had the exact same principle behind them, of taking a lot of water, pumping it, and delivering a very high volume at a very high pressure to wherever it needed to go. So the turbo pumps on the V2 rocket were actually based off of those pumps that were used for fire departments that had been used for decades prior. That's a really great example of where asking yourself these two questions can really lead to good success. And it's not necessarily even just a pure engineering perspective. There are historical examples to talk about whenever we talk about trying to solve a problem, and whenever we look at whatever's in front of us. As I like to say to people that I know, or as I like to say in general, is that no problem exists in a vacuum. There's always something you can derive by asking yourself these two questions as a foundation. And there's also very important historical lessons that come to these things, which is really what the meat of this lecture is going to be about. And they're definitely a little more on the more serious side of things, but we'll get into the first one. So the first example we talk about of history is one of the most important ways that we interpret what we're doing is the Apollo 1 fire. On January 27th, 1967, during what was called a plugs out test, it was just basically one of the final tests before launch, an early Apollo spacecraft, it was the Block 1 vehicle, was undergoing tests. And the crew were on board, they were running through it, there were lots of problems that sprang up, there were all kinds of issues that were coming. They were having trouble even communicating to the ground station in Florida just from the launch pad. And at about 6 in the evening, after almost an entire day worth of these tests, a fire broke out inside the capsule and killed the crew. And this was one of the most shocking moments in the Apollo program. Here we were 3 years before President Kennedy's deadline, and we had a system that didn't work and a crew that was already dead because of these decisions. And what were the decisions that led to this point? What were the root causes of that fire? You can talk about that from a very high level, which is that inside the spacecraft, the cabin was a pure oxygen atmosphere at 14 psi. And the fact that the cabin had lots of flammable materials on board. Now, these are engineering causes. These are, if you were going to ask an engineer what led to these problems, this is what they would tell you. But it's not necessarily the full picture, because there's a lot more beyond that we have to talk about, which is that at this point in time, the Apollo program is actually somewhat behind schedule. There was a lot of pressure on the company that built the command service modules in North American aviation to push out a product. And what that meant was that points where questions should have been asked, or points where things should have slowed down and a serious assessment should have been underway, they didn't happen. And it meant that the spacecraft was, as Gus Grissom, who was one of the astronauts killed in the fire, he there was a moment where he worked with a simulator and he hung a lemon on a coat hanger on the side of it, and lemon being slang term for a car that's not particularly good shape. All of those issues were manifesting instead of during testing, they were manifesting during like actual flight operations. Apollo 1 was supposed to be the first orbital flight of a command and service module in February 1968. Instead, it put the program back 18 months, as every single thing about the spacecraft was redesigned and basically fixed. The engineering problems were dealt with. The management and rush, that was something else entirely. It's very easy to fix engineering problems. It's not very easy to fix cultural problems. And right after the fire, Eugene Kranz, the very famous flight controller, gave a speech in which he wanted every single person in mission control to go up to the blackboard and write tough, and competent. Tough meaning that they would all be held accountable for the decisions that were made, that they would all have that sense of needing to, and to have a sense of accountability, a sense of that they were responsible for the decisions that were made. And competent means they wouldn't take a half-assed solution as an answer. Tough and competent. And that is something that, even as in a system as non-critical as an orbital launch vehicle, these are things that we also must remember. Because what we are building is a very complicated system. What we're working on developing is possibly the most complicated engineering project that anybody can undertake, second to building a nuclear reactor. And that's something we must remember as well. That when we're doing this, and in anything that we do, we are accountable for the actions that we have, and we should never take things for granted, that we should never say that this is fine, even if something isn't fine. And so that's what happened. After 18 months, the Block 2 version of the Apollo spacecraft was rolled out. The pure oxygen atmosphere at launch was eventually changed to regular atmosphere. Eventually changed to a regular atmosphere at 14.7 psi and slowly vented out as the crew ascended into orbit and eliminated the pure oxygen content. And then when it was in operation, the vehicle would have a 5 psi pure oxygen atmosphere, which is the same amount as in around us. It'd have the same amount of oxygen in the cabin as it would be in a regular atmosphere, which made things more a little bit more flammable and not as flammable as they were in a pure O2 atmosphere. And they also redesigned the spacecraft to have improved insulation, to have wiring systems that were incredibly consistent and very carefully insulated. They were, and all the flammable materials, anything that could even be suggested to be flammable, were redesigned and replaced with other more safe materials. And so the Apollo spacecraft went on to become one of the most successful ever built. The only time there was ever a major failure of the spacecraft as a whole was on Apollo 13, and that was a separate engineering problem. But even then, the toughness and competence came together to solve a problem that should not have existed, because it started systematically and it boiled its way down there. Engineering problems are never necessarily just engineering problems. Sometimes they are very much because of cultural choices, because of culture in the department or whatever the project is being worked on that says that you can accept this kind of failure. And that kind of leads us into our next part of our talk, which is a mere 20 years later. January 28th, 1986. Space Shuttle Challenger is sitting on the pad in Cape Canaveral, Florida, and is ready to launch. Schools all across the country are tuned in because for the first time, a teacher will be going to space as part of NASA's Goodwill Outreach program called Teacher in Space. The shuttle launches. Everything's just fine. The vehicle goes up. A few seconds after passing through maximum dynamic pressure, or max Q, as it's called colloquially, the vehicle disintegrates and kills all 7 astronauts on board on live television, grounding the shuttle program for almost another 2 years. And that moment is perhaps an even darker day than Apollo 1. Apollo 1 happened, and people that were directly involved in it were the main people that saw it, but this became national tragedy, a day of mourning, more or less. And the question is why? again, the realistic engineering consideration to be made is that the solid motors on the space shuttle could not be transported as whole units. They had to be split up into segments and then shipped by rail from their manufacturing facility in Utah out to Florida, which is really a long journey. And they had field joints. And these field joints had O-rings, a system of O-rings and flaps that would come together and prevent the hot gases from breaching the outside of the case. The day the Challenger launched, one of these seals failed. And the large liquid oxygen tank in between the two solid motors was right next to it. And hot gases came out and started impinging on the structure that held the solid motor in place. Eventually, the entire solid rocket motor swung forward on the cross beam and punched its way into the liquid oxygen tank, the head of the liquid hydrogen tank, and the shuttle's external tank, and the vehicle disintegrated immediately. The shuttle encountered aerodynamic pressures and forces in ways it was never designed, and the orbiter fell apart. The most haunting thing of all is that the crew were probably still alive and conscious the entire way down from flight altitude into the Atlantic. Nothing could have saved them. And the question is why? Engineering failures, as I said, are very rarely pure engineering failures. They are failures of management, failures of organization, failures of not trusting the right people. And that's part of what happened. The engineers behind the solid rocket motors on the day the Challenger launched, the day the Challenger launched specifically was one of the coldest that Florida had ever had. You could walk out onto the gantry around the shuttle and icicles, maybe that long, were hanging down from the sides of it. And the engineers that built these motors knew the limitations of those O-rings. And they went off to NASA management. They said, do not launch this. Do not fly this. You will kill the crew if you fly this. But the management ignored them because they had a timetable. The shuttle was supposed to be a vehicle that would fly so often and so frequently and have such fast turnaround times that it would be better than anything else. And the Challenger, the committee that investigated the Challenger accident actually found many other problems with the program that could have led to a similarly fatal decision or fatal moment, even without, beyond this. One of the most famous people on that committee was actually Richard Feynman, the physicist. If you read anything about physics in the early part of the 20th century, he's definitely a name that comes up. And one of the things that he did in front of Congress is he had a container of ice water, and he took a sample of the O-ring material and twisted it, held together with a clamp, and stuck it in the water. And he demonstrated how brittle and how inflexible the rubber became in those temperatures. In those conditions, the vehicle was not certified to fly. The O-rings would shrink very slightly. They would not expand to be the correct size. That means that if the motor is bent or twisted slightly, it could burn through and cause a catastrophic failure, much the same way that they actually did. And that's a very clear example of ignoring the wrong people. And it also presented something else as well, which is a concept called the normalization of deviance. And if you've never heard it before, it's a very important lesson to learn. You can think of the failures of a system almost like a bell curve, ideally, or the tolerance of a system to be like a bell curve. There are some environments in which things won't work either way, and there are a lot of environments where it probably will work within, say, one or two standard deviations in the middle. That it'll probably work here, but it won't work here. The problem is that if you start accepting flying or operating something in that domain, then you start in your head building up a new bell curve. And you start saying, well, it's normal that we operate in this domain. Things should be fine even if we push it. Things should be fine no matter what, but eventually you get something in just the wrong place. And it leads to a disaster. And again, we come back to Gene Kranz's famous words in 1967, which were echoed by the director of NASA talking about the Challenger disaster. Tough and competent. Competence, meaning you should never take things for granted. Competence. Competence failed. And it's this exact same principle, this normalization of failure, this acceptance of things operating in a domain where they probably shouldn't be, that also caused another very famous loss of the space shuttle in 2003. Space Shuttle Columbia was the first orbiter ever built. It made the first flight of the shuttle program on April 12, 1981. And when it was making its flight in late January to early February 2003, it was probably going to be retired as the International Space Station took more precedence. But it was still able to fly by itself and operate a little space lab on board. The shuttle was prepped for re-entry. It deorbited successfully. It flew through the upper parts of the atmosphere. But then people in the early morning skies over Texas watched it shredded apart. The crew never made it home. And it was because of something called foam strikes. What happened was that big external tank in the shuttle was covered in a layer of insulated foam. And occasionally during flight, little tiny parts of it would chip off just due to aerodynamic forces. And sometimes they'd go and they'd be completely harmless, and sometimes they would smack into the shuttle orbiter. Anytime where you have the phrase, bits of the rocket are falling off and hitting the most important part of the rocket, should be cause for alarm. But eventually it was realized that nothing could be done about it. That this was the way the shuttle was built. There was very little that could actually be done to mitigate these foam strikes. And there was an incident shortly after Challenger in which a particularly poorly placed piece of foam hit the wrong part on the underside of the shuttle, and it almost burned through and killed the crew on re-entry, but it was protected by a very large piece of aluminum that was directly behind that. The worst part was it was a Department of Defense mission, so there's really not much that the general public would have known about it had it happened. And yet, it was accepted. Foam strikes were accepted as part of the danger of launching the vehicle. And it just happened that the way that the orbiter was set up, let me see if I can clear this up. The way the orbiter was set up on the stack was something like this. And there's something called the bipod ramp, which is right underneath this part of the shuttle. It was an aerodynamic fairing that was put in place to help protect the front lines and the mounting points for the shuttle on the external tank. Part of that chipped off, went into the airstream, and struck the leading edge of the shuttle planes. That is a particularly critical failure because the panels that were on the leading edge of the shuttle were the parts where it got the hottest. So NASA used a material that was incredibly heat tolerant but very brittle called reinforced carbon-carbon. So this suitcase-sized piece of foam, I'll use my actual briefcase as kind of an example, something this big, hit the wing of the shuttle with a pretty good clip and punched a hole maybe twice this size into it. And the crew had no means of detecting it. Could never have made it home. And that's what happens with normalization of deviance. If you start getting comfortable with the fact that this is the way things are, and even though it sounds bad, it's not bad. And that moment was a particularly gruesome and shocking tell of when normalization of deviance can itself become the problem. And that was the moment that ended the shuttle program, more or less. The Augustine Committee came together in 2003, analyzed the problem, and recognized that the vehicle was just inherently unsafe, and they could be wound down in response to a new program, which is exactly what happened. And I think one other takeaway from the Challenger disaster as well is the idea of public relations. NASA had a very hard time in the 1970s. After the Apollo program, most of the general public tuned out NASA and ignored the exploits. In fact, I would argue that most people would say we only went to the moon once. We went there 6 times. Sorry, yeah, 5, 6 times, depending on how you count. And the general public grew tired. There was a war in Vietnam that was generally unpopular and caused the government to hemorrhage money. And budget cuts had to be made, and then a recession happened. Gas prices went up. If you ask your folks about gas rationing, they can probably tell you about that time. Gas stations literally had no gasoline some days. That's how bad it was. Gas prices hiked for the first time. Energy was more expensive, and the government had to start making cuts. And it started with the Nixon White House in 1969 approving the shuttle program. It was supposed to be an integral part of a space transportation system. It was supposed to have things like nuclear thermal propulsion tugs of space stations around the Earth, around the Moon, and maybe even around Mars. But eventually it was reduced down to just the orbiter component because of those cuts. So NASA had a hard time entering the 1980s. They had to justify the expenditures that were made on such a complicated and expensive system. And it it started with that, and it started with NASA trying to do public relations. The crew on the shuttle was advertised as being so safe that you didn't even need to wear a spacesuit to get on board. You just needed a crash helmet, the microphone. And that's what they wore walking out on the ramp to board Challenger. No pressure seats, nothing, no escape systems. It was supposed to be as safe as an airliner. And it was revealed later on that NASA, using modern approximations for loss of crew, loss of vehicle events, which is a situation in which the crew is killed, that the loss numbers were as high as 1 in 200 when the shuttle program started out. NASA's understanding of them at the time was closer to perhaps 1 in 1,000. And its lesson there is really, why do we worry so much about safety? It's because of that. It's because if you cultivate a culture in which you can accept this as you accept the deviant, right? And you accept that things will go wrong, and you don't think about the repercussions of those things going wrong, then you put yourself into that position. And it's a strong sign that you should never try and twist your numbers into, and this is something that applies even beyond what we're talking about with building a rocket. You should never twist your numbers. You should never lie to your management, lie to the people you're advertising to. You should be as honest as you can as humanly possible, because sometime, at some point, those numbers will line up just the wrong way and something terrible will happen. And let that be a major takeaway from this entire lecture series, is that, to quote Kranz, you must be tough and competent in all that you do. But talking about historical engineering isn't necessarily something that we need to be so serious about, because there are moments in which systems have performed above and beyond the call of duty. And because of smart engineering and smart decision making, people's lives have been saved. I think the most interesting example of this, or one we can talk about in two different directions, is the very recent failure of a Soyuz spacecraft to launch. It was October 11th, 2018. A crew of 2 were getting ready to launch to the International Space Station. 1 Russian cosmonaut and 1 American astronaut. The vehicle lifted off just fine. It went through its descent profile, and if you've never seen a Soyuz spacecraft, the launch vehicle, it looks something like this. Sorry, screw that up a little bit. I'm not an artist. It looks something like this. And the way that it works is that this core stage burns for a very long period of time, and these outer boosters come off, and it keeps burning, and then it stages into the second stage, and the spacecraft is up here, hanging out with the crew on board. So what happened was, is when it came to the separation point, the vehicle basically disintegrated. This is actually called stage 2 in Russian parlance. Stage 2 just evaporated. And fortunately, the launch escape system, not the full tower, but there are secondary motors built into this part here, was operational and still on the vehicle. And all it did is it lit the engines, blew some explosive bolts, and the crew rocketed away to safety. It was a very unpleasant ride. They pulled about 20 Gs or so, but the crew was perfectly fine. They landed a couple miles downrange. They were rescued just fine, and they went to the International Space Station about 6 months later. And the difference between this and the contrast between the successful rescue or a successful failure of a system like this and the ones we talked about earlier almost completely revolves around designing a system that is capable of either working when most of the parts don't work, or a system that will save the most important parts even at the sacrifice of the mission goal itself. You're not getting to orbit if you're pulling it aboard, but if you have that system on board, you'll be really thankful when you need it. It's like having a seatbelt in your car. And what happened was, it was later determined that one of the ball joints, because there's a joint here that allows the booster, because it kind of looks like this, it hinges out, and then it flies away as this depressurizes. It goes because it's actually held together with straps back here. So it's supposed to do that, but this ball joint was malformed in some way, and it stuck in place. It caused the tore apart of the second stage, and it resulted in an abort. And that's a very valuable lesson, too, is that you have to be careful about the kind of quality of parts you accept, because when this happened, if you don't remember, back in 2018 was a pretty rough year for the space program, it has been for a while, is because they've been producing and installing subpar, poorly contracted out parts over the last few years because of regional political issues, instability, the lack of jobs, et cetera, so on and so forth. So there is a real reason why these things are happening, and I don't feel like blaming engineers for this, but you have to be willing to trust and accept your suppliers, is really, I guess, what the big takeaway out of this one is. You have to be willing to design something that works in this fashion. You can't trust the reliability on a system this complex that has to work all the time and has no fail-safe mode. And I really want to stress that, is that a plane has a fail-safe mode. If the engines break on the plane is still a glider. If the engines break on a rocket, the rocket is a ballistic object. It does not glide. It does not have any position you can put it in which it'll come back in one piece. It will disintegrate. You can't trust the system as a whole if it's something incredibly valuable like human lives. You have to be willing to accept, and it's not a sign of poor engineering by having a system like this. It's a sign of good engineering to have a safety system. And most spacecraft have had a very similar safety system. So we talk about something like Elon Musk's Starship project, the idea of an integrated spacecraft and crew and all that other into one vehicle. Something that you might ask is, well, why don't they do that with all rockets? And this is pretty much why. We demonstrated between the shuttle failures and the Soyuz and the success of saving crew from an abort that these systems are critical, and you need to be willing to accept this. I really fail-safe. It's not this rescue system, basically. Otherwise, you'll be in a position in which you have to trust the reliability of the whole system, and that will not always be the case, no matter how good you get it. So, which I think is a very important lesson to learn. And of course, there's another great example of hardware being used above and beyond the call of duty. Designing a system that is so fault-tolerant that even when everything goes wrong, you'll still get your people back home and you'll still have a successful flight. So what was perhaps considered to be the finest hour of any space program in history, in this particular case, well, it wasn't NASA, was the successful failure that was Apollo 13. For those of you who don't know, in April 1970, Saturn V carrying 3 astronauts, one of whom was a veteran of, actually the astronaut who spent the most time in space out of anybody on the surface of the Earth at that point, and 2 rookies, were traveling the moon, going to go to the Framoro Highlands on the surface. And while they were passing through the gravisphere influence of the moon, they did an oxygen tank stir. There were these cryogenic oxygen bottles on board because the Apollo spacecraft had fuel cells. It reacted liquid oxygen, liquid hydrogen to make electricity and water, which means you had drinking water as a byproduct, which is great for any system like this. But it meant that you had to occasionally stir the tanks a little bit because they could propel the liquid would settle or slosh around in microgravity. You wanted to be sure that there was fluid in contact with the drain valves and make sure you weren't getting any hot or cold regions. So you had a little stirring mechanism, a little mechanism that would just make sure it didn't stratify. And during an oxygen tank stir, one of them blew up. And it completely knocked out the environmental control systems on the command module. And they were already on the way to the moon. They still had to go around it. They couldn't just turn around because nobody wanted to touch the very large engine at the back of the command and service module because they were worried it was going to blow the whole thing up. It could have been damaged. In fact, in photography on the way back, the bell was visibly dinged from the panel that had lobbed it, ripped itself off from here to here. So that was a pretty big crisis moment because you're on a spacecraft that is rapidly running out of life support, and you have to go all the way past this object that is, 250,000 miles away from home, and then come back around again because you can't do an about face with the engine you have available. But there is something very fortunate. That all of these various factors, all of these engineering decisions, even the ones coming from the Apollo 1 fire, which was at that point 3 years earlier, the idea to insulate all of the electronics, the idea to design a system as fault-tolerant as it was, came together in this moment to allow the crew to make it home safely. And they went through so many pratfalls in trying to do this. They had to, first problem was they had to try and stop the leaks, and they shut down reactant valves that would cut off the electrical supply, and they did that, and it didn't solve the leakage problem. In fact, it completely drained out, right, which means they couldn't go for a landing. They had to crawl into the LEM, which was only designed to support a couple people for a few days, and they had to make like a week or more, almost a week out of it. They had to crawl into the lunar module. They had to take advantage of its life support system. This was perfectly functional this entire time. And then when they got back to Earth, they would have to power the command service module back on because they were only running on batteries at this point. So many things happened. If you've never seen Apollo 13, the 1995, 95 film with Tom Hanks and Ed Harris and all those other great actors, you really need to see it because it's not completely true to life because no film is, but it's a really great depiction of the story. And long story short, because of all these decisions, this ability to come together and make a system that would work and had all these redundancies built in, they got very lucky part of it, but the other part was great engineering. They were able to bring the crew home safely. And remarkably so. The root cause, for what it's worth, was the oxygen tank had a damaged insulation on it even before the vehicle was flown. It was actually dropped. It was really supposed to be installed in Apollo 10's service module. But they dropped, and they were like, nah, we need to test this and verify that it works. And during the testing, it damaged the insulation on the heating and stirring mechanism that was built into it. So at just the right time, it was basically a ticking time bomb. Just the right time, and that was that. But it's really, the story in and of itself, which I feel like I can't really do justice to. I can basically talk about the specifics of what happened. It is an incredibly remarkable example of problem solving, of engineering, of trying to fix issues. There's the famous moment with the carbon dioxide scrubbers on the lunar module. They were designed to accommodate a cylindrical unit, and they only had a couple days worth because they're only going to be on the surface of the moon for 2 or 3 days. The ones in the command module were much bigger, square. So they had to build an adapter using nothing but the supplies on board the spacecraft that would allow them to install the carbon dioxide filters from the command modules. They had plenty of, because you're going to spend an entire week or more on that, to the systems and life support systems in the LEM. And they did. They had a ground team that literally put the thing together, came up with instructions for it, and then they got someone in the console chair to talk about what they were doing. They read through the protocol. It's basically communicating with a completely separate room of people. You can't show them directly, you have to tell them, and they built it successfully. And it's a testament to the ingenuity of engineers, it's a testament to the problem solvers, and a testament to effective leadership and smart design decisions, and designing a system that will work even if the worst possible scenario happens, like this, which is pretty much as bad as you could possibly get in the Apollo spacecraft. It still worked. And they got the crew home safe, which is a really remarkable thing when you think about it. So it's a very valuable lesson that you can't design systems that aren't tolerant to these things. And that's really what I wanted to focus on, is the question of what can history tell us. There are so many examples throughout spaceflight history of design decisions being made, of choices being made, of failures, of successes, of all of these complexities. And you have to really be willing to familiarize yourself with those things. Because it's not copying if you're trying to learn from what's already out there. Otherwise, you run the risk of repeating tragedies that could be easily avoidable. You have to know where you're... As someone once said to me, you have to know the rules to break them. And that's very true, even when it comes to something as complicated and ridiculous as trying to build an orbital rocket. And the second little part, which is, what can an analogy tell us? I want to talk a little bit more about that as well. I know the lecture is called the Historical Engineering Context, and analogies really aren't the history per se, but they are also really important to try and understand. I talked a little bit about one of the most famous examples, which was von Braun looking at the problem of trying to get lots of propellant into a combustion chamber and looking at using a turbo pump from a fire department to do that. That's solving the problem by analogy, and there's nothing wrong with it. There's absolutely nothing wrong with saying what has been done before. And there are companies and organizations out there, and there are problem solvers out there that have used an analogy to try and solve issues in front of them. A very big example of one of these is actually what SpaceX does with a lot of their flights. They will use off-the-shelf hardware in parallel as I talked about in the second lecture, the coring voting system. They'll use off-the-shelf hardware in conjunction with that. because the difference between space hardware and regular consumer-grade hardware is mostly the fact that it's made to be more redundant. It's meant to function in a more hostile environment, but you can control for those in some way. You don't really need to worry about that. And it's important to be able to be willing to work on things by analogy. There's nothing wrong with looking at what other people have done. I know people that are very obsessed with trying to solve problems and never look at anything anyone else has done so they can try and figure out by themselves. But the reality is that, as I said, no problem exists in a vacuum. There has been no issue or situation that hasn't already been touched upon in some way, shape, or form, even in a slight sense, by other people trying to solve similar issues. But that's, of course, not to use other people's solutions as your own, because that's also not really a great way of doing it. Let's see if I think of a good example off the top of my head of doing this. Well, I guess software is a really great way of talking about it, because software, there's lots of other ways to solve a problem. There's lots of other ways to look at something and say, okay, this is what other people have done, I can just use this. But it won't work all the time. You can't basically look at one solution and use that as your only solution, because you will never come in. The reason why it's by analogy and not by direct comparison is that you can have situations. How do you pronounce that? Analogous. Yeah, that's analogous to. I don't know why I couldn't think of that word. It's analogous to a certain situation in front of you, but it's not a direct drop in. And let me think of a really good example of that. I had one in mind, but it fell out of my head. But anyway. You can't kludge something into working. Sometimes it becomes necessary that you can't just force it. You have to actually start from scratch and come up with something using that as inspiration. That's really true in a lot of software, solving a lot of problems in software. And because there are so many solutions out there. And you can find libraries, especially for object-oriented programs, you can find libraries of things that people have come up with that people do use, but it may not cover all of your bases. And I wish I could speak in less general terms, but software really ain't my personal strong suit, so I'm not really going to talk about that. But it's something rather important, and it's something to keep in mind when you're dealing with these. Because as we talk about developing an orbital launch vehicle like this, we are more or less looking into a novel domain that has some comparisons, like the flight trajectory stuff, and calculating that. It's been done before. There are other groups that do it. It's very similar to the kind of equipment you find in high-powered rocketry, but it's more analogous unless a direct comparison. You can't use off-the-shelf altimeters in a rocket like this, because off-the-shelf altimeters, for example, have a barometric pressure sensor that determines altitude. And the barometric pressure sensor basically registers the pressure of the air around you and either compares it to a lookup table that's installed on the board already and says, oh, I'm at this altitude, or it uses the change in pressure with respect to altitude and calculates your position based off of that. And the thing is that those systems tend to fuzz out at around, 30,000 feet. Space is a lot higher than 30,000 feet. So you can't use that direct system. You can use an analogous system, which is, say, a sensor that uses acceleration as a function of time and takes the derivatives of that, and you get your velocity. You can compound that across the entire flight profile and get an idea where your position is from that. And it's a similar concept of using change and rate of change in solving the problem, but you can't use the exact same hardware in it. And that's, I think, a really great example of analogy in hardware engineering. So I've talked to people that have built very high altitude altimeters, and they don't use barometric sensors because you just can't. So, and you'd be foolish to say, well, this is how we're going to do it, and just chuck it in there and call it a day, which is why there's the balance between analogy and direct comparison. You can't really do a direct thing all the time. You can do analogy a lot of the time. And it's just really, really important to keep that in mind. But of course, we talk about the idea of first principles. That's something I mentioned at the very beginning of this. And I've said that it's not necessarily the best way to solve a problem, but sometimes it's the only choice you have, especially when it comes to trying to come up with a software solution. And it's really something you can only use once you've exhausted those two things. Both of these, I talked about the history. The history is incredibly important. That's why I called this historical engineering context, even though it doesn't really seem like a pure history lecture. The history is so important to understand because it shapes your understanding of what you're talking about. And it shapes the amount of information you have available, and it shapes the solutions you can come up with. You can only know so much yourself, and you can only determine so much through intuition. You have to eventually say, what have other people done? And you have to eventually say, what are the lessons that have been learned in this process? Because you'll retread the same path, you'll make the same mistakes. And if time is a critical element, as I talked about in the product triangle in the second lecture, if time is such a critical element, then you cannot afford to shift time in favor of iterating through a design. You're almost better off just using another system, commercial off-the-shelf system that's available and you can purchase directly. And that's a great example of kind of playing with both analogy, direct comparison, and history. You really need to have a good understanding of all three of those things. And I think that the best innovation tends to come from successfully balancing those things, especially by analogy. Like the assembly line, for example. The assembly line as a concept was derived, existed sort of, but was more or less derived from looking at a meat packing plant, imagining it in reverse. It's not something you immediately think about. It's a system that was optimized years before, but it's brilliant in hindsight. And that's where it came from, looking at something by analogy. And I think that's really the best way to solve problems. So I have a little bit of like a tangent to go on at the very end of this lecture because I think it's really good to summarize a bunch of things and talk about the long-term effects of this series. So this may seem a little bit off topic, but I think exploring the history of these points is the main focus. I think it's really important. That's why we call this historical engineering context. But there's something I really want to get into when it comes to this project as a whole, which is, or this lecture series as a whole, which is, I can't teach you everything. I am a geologist in a suit who has 10 years of experience being a lawn chair spaceflight fan. And I cannot sit down and explain every single possible avenue or approach to take when it comes to solving problems. The best that I can possibly hope to give all of you, and if you're watching this in the distant future, you as well, is the desire to learn more with the right tool set in mind. I can give you a bag of tools. I can tell you how to use those tools, but I can't tell you how to build a house. And this is now the point in the series in which I emphasize the history and historical context, which is that there are so many wonderful resources out there that you can go off to the libraries, off to Wikipedia, off to Encyclopedia Astronautica, off to all these other resources and get a really good understanding of what has already been proposed and done. And maybe in the description of this, we'll put together a little list of some interesting or important links, but I can only go so far. I can only give you a torch to carry in your hand and open the door to a very vast and complicated library full of things you may not care about, you may care very deeply about, that may or may not be important, but that's entirely up to you. And I think the first really big example of this, and I think I pulled this out during the second lecture, is, or at least a wonderful starting point, is Ignition by Jonathan D. Clark. Rutgers actually owns the publishing rights to this book. This was a custom copy that was printed for me by a very dear friend over in, I think, Michigan or something to that effect, who owns a book printing thing. It's derived from a PDF that was available online, but it got cleaned up from there. So this book is a very good and interesting resource because it's not just about the pure science of it. It talks a lot about the history behind it. And the history is, as I said, one of the first tool that we have in our tool set of solving problems. So we want to talk about, well, how can we innovate upon propellants? Well, look at what other people have done. And I just love this book anyway, so I recommend reading for me. Another one is Sutton's Spacecraft Propulsion Elements, which goes into a lot of the math and the complicated stuff that you figure out over the years. It talks about even involved things like designing rocket engines yourself. That's a very valuable resource. But the most important one, I think, for a lot of our purposes is actually going out and talking to people that have built high-powered rockets. I have some experience in high-powered rocketry myself. I know the forums, I know some of the people that are involved in the field, and I've talked to a lot of people in the field. And understanding that is by analogy, because they've built rockets that go up very high altitudes. I think the current record, except for Go Fast and whatever the hell US CRPL called their rocket, the amateur record is in the 6-digit foot range. It's like 150,000 feet or something like that. It's really high up. And that's a domain where you start talking about the little Estes kits that you buy at the hobby shop, and you start talking about, well, the big orbital thing that we're talking about. And it's very important for you now, as I've concluded this little lecture series, to actually go out into the world and start playing with those things. Because I've given you the tool set you need, as I said. the most important, basically, long story short, the most important lesson I can give you is that you should never stop trying to learn. And that's even in something like this, because we're all learning together. Working on the project such as an orbit-capable rocket is not easy, and it's not going to be something I can give you the how-to guide for. But the most I can hope to do is to start a fire in your minds and go out there and start learning more about how rockets work, how to build them, how to fly them, how to pay for them, all those kind of things. And it's my hope that during this journey, that even if we're not successful, even if we don't manage to get a rocket into orbit, even if we don't build anything of merit, I think it's so important that we are willing to learn, to never stop learning, never stop asking questions. Because that's how you do great things. You don't start to do great things by starting out and saying that you're going to be great. You do great things by doing something cool really, really hard until you become great. You don't start out with a passion project by saying that you are going to do this thing to prove yourself. You do it because it's cool. You do it because it's something that personally fascinates you. You do it because it's something you're in love with. You have to have that passion because you need to be passionate about the things that you're doing. And I hope this lecture series has in some ways both taught you some fundamentals about concepts with orbital rocketry and dealing with the complexities of the math, of the science, of the history behind it. And I hope it's inspired some of you to keep learning and to never stop learning. It's been a great journey. I'll catch you in the next series. My name's Matt. See ya.